Everyone for holding on. I am actually going to share my screen before I give it back to Doug. So welcome to today's Cultivating Success webinar. We're really glad that you joined us today. Our topic is ecological soil management, and this is an introduction to both soil science and managing soils. And as you can see, our presenter is Doug Collins. The Cultivating Success program was established by University of Idaho Extension, the Washington State University Food Systems Program, and the nonprofit organization Rural Roots. This is our fourth year of doing our annual webinar series, and we're really delighted to have a partner from Washington State University join us. So Doug is an extension specialist and a soil scientist in the Center for Sustaining Agriculture and Natural Resources. He's located in Puyallup, Washington, which is on the west side of Washington, and he has been a longtime leader in the Washington Cultivating Success program. I'm Colette D. Phelps. I will be your moderator today and be helping with questions. Mackenzie Lawrence is also with the University of Idaho. She's on to provide technical support, and you already saw how great she is at doing that. Just a couple of webinar tips. We're sharing so much bandwidth these days. If you close all of the other programs that are running on your computer, that might help with speed of transitions in sound. If anytime you're having sound issues, you can use the call-in number provided in your welcome email. If you do that, just make sure that you mute your computer so you don't get feedback. This is webinar format, so any questions that you have for Doug, please type those into the Q&A box that you will find in the control bar. For most devices, that control bar is at the bottom of your screen. Sometimes if you are on an iPad or a phone, you might find that at the top of your screen. There is also a chat box. If you need help with any type of technical assistance, you can use the chat box. You can also use the chat box just to share general comments or to talk with other people during this webinar. So please feel free to use it that way. This webinar is being recorded and will be available on the Cultivating Success website. And I will show you exactly where at the end of this program. So with that, I'm going to stop sharing my screen and go ahead and hand this back over to you, Doug. Thanks so much for being here today.
Thank you, Colette. It is a pleasure to be here. Just check if that looks good to everybody.
That looks great.
Okay. This is, I should say, actually, this is the wrong title. We're going to talk about managing and monitoring soil fertility, but it's part of a larger presentation, ecological soil management, an introduction to soil science. And just quickly to tell you what we're not talking about today are some foundational soil principles that would traditionally be covered, and hopefully these are things that you know something about. So what is soil? What's in a volume of soil? Sort of how we go about studying soil science, and then those soil forming factors. So we won't go into those. Hopefully you've had some of that before, or you can read up on that if you would like, and we can certainly get into that if we have some time for questions. So I'm going to jump right in and talk about soil function, and then go into some of the soil organisms that are responsible for functions. And then we will look at soil nutrients, how nitrogen and nutrients cycle through the environment, and then some soil testing tips and practices. So soil function is the ability of soil to provide a service. And if those services are no longer occurring, then we think of that soil as degraded. And if a soil is functioning well, we think of that soil as more or less healthy. So what does healthy soil do for us? This is the part where I would love to hear some audience feedback and hear what you know, but I guess I'll just have you think about it for a minute in your minds. What does a healthy soil do for us? And hopefully you're thinking about things like nutrients, getting nutrients to our plants, suppressing root diseases, allowing roots to penetrate that soil and develop a healthy root system, allowing water and air to infiltrate easily, and then also holding on to water during those dry spells. So holding water and then providing it back to plants during dry spells, and then supporting beneficial organisms like mycorrhizae. And then another important concept of soil health or soil quality is what's the context. So if you're going to build a house or a sauna out in your backyard or something, what you're going to put that on soil, and your expectations for that soil are different than if you're growing plants. So the capacity to function depends on what it is we want that soil to do. So, if you're looking for soil to support structural buildings and roads, you're going to have a different definition of soil quality than in an agricultural context. So this diagram shows kind of a hierarchy of terminology that can be used to describe soil function, especially in the context of agriculture. At the base are soil tilth and soil fertility, and that gets to the physical and chemical attributes of soil. So how do the physical and chemical attributes of soil affect soil function? So these are like soil supplying nutrients, allowing water and air to infiltrate, so that soil tilth, or that physical properties, the aggregates in the soil are very important, providing air and water infiltration. So that's sort of the core of soil health discussion, and then providing that water. So those are the tilth and fertility. And then higher up on the hierarchy here, productivity is something that is frequently of interest to agricultural producers. When we're talking about productivity, we are talking about generally yield per acre. How much can we get from the soil? And so that's affected by tilth and fertility, but also by light, plant pathogens, if there was any history of herbicide use, and other factors. And so productive soils develop healthy root systems and help suppress root diseases. At the top of this hierarchy are soil health and soil quality. And assessments of soil health, is sort of a distinguishing factor between those two, is the importance of that biological component. So, I mean, you can pretty much use soil health and quality interchangeably, but when we do talk about health, we do tend to think a little bit more of that biology. So supporting mutualistic relationships like mycorrhizal fungi. And then another important component of soil health and soil quality is that we're able to, so these soils have the capacity to function, but they do it through time, and also without harming the external environment. So if you think about this hierarchy, you could have a very productive soil. It's got a lot of fertility because you put so many nutrients into it. But if those nutrients are leaking offsite into groundwater, into surface water, degrading the external environment, then we certainly wouldn't call that a healthy soil. So degraded soils are soils that lose function, where that function declines or is disrupted. So things like compaction are going to affect that soil tilth. And this can be done by excessive tillage or driving over the soils. Chemical degradation could happen from salt buildup. We see this a lot of time in potentially hoop houses or drier environments. And then just loss of biodiversity and organic matter. And again, I mentioned this, but if nutrients are being lost off site, then we certainly don't call that a healthy soil. So this is an example of phosphorus overloading into fresh water. Phosphorus is a limiting nutrient in freshwater ecosystems. So whenever phosphorus gets into freshwater ecosystems, we can see an explosion of life. And then when those organisms die, those algae, they sink to the bottom of the water body, and they start to consume oxygen and really negatively affect the water quality. Another concept for soil function is the concept of inherent versus dynamic properties. And so inherent properties are properties of the soil that we cannot change through human influence, basically. So those are things that are determined by soil forming factors and change over thousands of years. Things like texture, depth of the A horizon is difficult to change, depth to bedrock, for example. These are things that are inherent. So one soil is not necessarily, some soils are just better than others, I guess is one way to think about it, because of their inherent soil properties. The mineralogy is another inherent soil property. So what was the parent material of those soils? That can really affect the innate soil fertility. So some soils have more innate soil fertility because of the parent material that they were derived from. And then on the other hand, dynamic soil properties are things that can be changed, not necessarily easily, but they can be changed through management. So those are things like bulk density, some soil properties, things you can go out and measure: the bulk density, the organic matter, to some extent nutrient cycling, soil structure and infiltration. Some of these really cross over both inherent and dynamic, but soil structure, again, the aggregation. Soils with more clay are going to more readily form aggregates, but if we manage soils through less disturbance, through more organic matter, we can build aggregation up to a point. And the other thing about dynamic soil properties, so they can change over a season, over a couple of years, sometimes even over the day. Something like temperature could be a dynamic soil property, and we can see big changes of those in short amount of time. So, or a lot of these functions, especially when we talk about nutrient cycling, also, as we'll see with aggregates, these are things that we say soil does, but really it's, what part of the soil is making this happen. And the biology, the life of the soil really does influence a lot of these functions. So this is a diagram that many of you may have seen. This is a diagram, the soil food web, and what this focuses on are what we call the trophic levels of organisms in the soil. So we've got our primary producers, the photosynthesis, and then things that eat the plants or organic matter, the dead things, the decomposers, and then things that eat those things and things that eat those things. So this is sort of a who eats whom kind of diagram. And this is a really good way to think about energy flow through the soil ecosystem. As these organisms are eating, they're excreting waste, and that's creating more nitrogen. So we'll go over that a little more later, the nitrogen cycle. But I do want to call attention to what's missing from that sort of classical soil food web diagram. And that what's missing from that are these larger bodied organisms that have a larger presence or an effect on the soil. So primarily among those would be things like earthworms, which we call ecosystem engineers. And then millipedes and springtails, we call those shredders or litter transformers. So this is sort of taking organisms in the soil and dividing them into these different guilds or groups. And you can see that the primary consumers and the secondary consumers are sort of captured in that first model, but what's not captured in there are the organisms that have these cascading effects. So like the litter, the shredders, the organisms that are out there sort of transforming the environment or the soil. So litter transformers are important because they speed decomposition through an external rumen. And they, if you know what a rumen is, that is something that ruminants, cows, sheep, goats have. That allows them to feed on grasses and then get lots of nutrients from that. And it's really the bacteria in their gut that is helping them to get those extra nutrients. So, the decomposers like bacteria are uniquely capable of breaking those atomic bonds at the level to release nutrients. So these organisms with their external rumen, they hired a really good PR firm when they came up with this term, because what that means is that they will go about and ingesting this raw material one time, and then they'll leave behind fecal pellets. And these fecal pellets are much more easily colonized by bacteria that live in the soil or fungi. And so they'll colonize these fecal pellets and they'll do their degradation of the material. And then these organisms will come back around and re-ingest those fecal pellets. And the second time through, they're getting a lot more energy from that material. So they speed decomposition by cutting the material up into smaller pieces, making it more more easily to colonize by microorganisms. And then they're also spreading the material to different places. So they're speeding up decomposition through this sort of mutualism with external microorganisms. And then earthworms, we call them ecosystem engineers because they're changing their environment to suit their physiology. And this is sort of an interesting story. The reason that earthworms are sort of doing what they're doing in the soil, and here we're primarily thinking of the larger bodied earthworms that sort of build these burrows up and down the soil. They are doing this to help answer nature's call. And that's because their physiology is much more similar to freshwater organisms than it is to terrestrial organisms, where terrestrial organisms will excrete really small, dilute amounts of waste urine because they have kidneys. Earthworms have nephridia, like a freshwater organism. So they have to basically excrete about 90% of their body weight in water every day. So they really like a much more moist environment. And most of their cousins, we call them earthworms, they live in the soil, but most of their relatives are actually freshwater organisms. So they made this leap to land, but rather than doing the sort of evolutionary adaptation and changing their system, they started to change the soil to basically behave like a kidney for them. So they move up and down through the soil to find environments that are at the just right soil moisture. And that's why we find them very deep in the soil in the drier parts of the summer. And then again, they are compressing soil together to cause aggregates, and they're building these channels, which allows water to infiltrate more easily. And then their fecal pellets themselves are really stable aggregates. So when they create this more aggregated soil environment, that allows water to infiltrate and creates sort of a broader zone in the soil for them to find that zone of just right where they can get their basically matches their physiology. And so the key part about these organisms, the earthworms and the litter shredders, is when they're removed from a soil ecosystem, their function that they provide is completely removed. So a function like decomposition is not something we're going to lose through tillage. Bacteria are very small, they're very robust, and they're not going to be wiped out from tillage. But larger bodied organisms, from excessive tillage, from poor soil management, we see those being essentially eliminated following those events. All right, so transition to soil fertility and nutrients. And I presume this may be a review to some people as well, but so fertile soils are soils that are capable of providing nutrients to plants. And the definition of a nutrient is it's an element that is required for plant growth. And so we have macronutrients. There's about 15 or so nutrients, required elements. Macronutrients and micronutrients, you can see that what these numbers we're looking at are percentages by plant dry weight. So most of what a plant is made up of, about 96%, is carbon, oxygen, and hydrogen. And these are not what we would call soil nutrients. They get carbon from the atmosphere through CO2. They're also getting oxygen that way. And then they're getting oxygen and hydrogen from water, both from the above ground, but also through the soil water. And then the other macronutrients, the definition of a macronutrient is that it just occurs in plants at higher amounts. So again, the definition of a nutrient is it's required. So micronutrients are just as required as macronutrients, but they just occur in much less amount in the plant. So plants need less of it. In fact, a seed is going to have enough nickel for probably several generations of a plant. But if you can manage to grow a plant without nickel, you'll start to see some nickel stress. So we do, and I will talk quite a bit about nitrogen today, and that's because you can see that it's the soil-derived nutrients that plants require the most of. So whereas phosphorus is typically the limiting nutrient in freshwater systems, nitrogen is almost always the limiting nutrient in terrestrial systems. Okay, so not only must a nutrient be in the soil, but it has to be in the soil in a form that plants can take up. And I have looked at some roots. I haven't done a lot of root work. It's very difficult. But the roots I've looked at, I haven't seen a lot of teeth on those roots. So the roots, the plants are not chewing away at the soil in order to get these nutrients that they need. Instead, roots are much more like a straw, and they're pulling nutrients in with the soil water. And so in order for a nutrient to make that journey into the plant root, it has to be soluble in water. And in order for an element to be soluble in water, it has to have a charge. So if you remember, one of the great characteristics of water is it's polar, it has both positive and negative charges. So water can really solubilize negatively or positively charged elements. Positively charged we call cations, negatively charged we call anions, but they have to be in this ionic form in order to be taken up by roots. And so here are some of the examples of types of elements or compounds that are taken up, that are soluble and taken up by plants. So with nitrogen, we see the positively charged ammonium, or probably much more commonly, the negatively charged nitrate. And then some elements like potassium, calcium, magnesium, they exist in what we say their free ionic form. And then things like phosphorus are complexed with oxygen and hydrogen to create phosphate. And this just shows the importance of water. So, your soil, you can have lots of nutrients and lots of available nutrients in your soil, but if the soil is totally dried out, again, that's going to inhibit plant roots from being able to get that nutrient. So water is sort of one of those master variables that can affect fertility, as is pH. Just a quick, we'll talk about pH a little more with soil testing, but just real quickly, pH measures how acid or alkaline a substance is, and it's related to hydrogen concentration. So if we have more hydrogen in the solution, then we call that a more acidic environment. And if there's less hydrogen in the solution, then it becomes alkaline. And in terms of nutrients, phosphorus is one of the ones. So what this is showing, where the fat area is showing, this is showing how pH affects nutrient availability. And the fatter area means more available. And so phosphorus is one of these that it gets pinched off at the very low end. And then it also gets pinched off at the high end. And this is because instead of being dissolved in the water, it precipitates. So at the low end of pH, it's going to precipitate with aluminum or iron. And then at the high end, it's going to precipitate with calcium. So once that material precipitates, it's no longer available. So phosphorus is very sensitive to pH. You can see, we call these kind of the metals down here. So manganese, boron, iron really fits this profile. Those tend to be more available at lower pHs. Look at that iron. So much more available at lower pH, less available at higher pHs. And so that's the concept for most of them, but phosphorus also loses availability at high pH as well. Okay, so we are going to talk a little bit here about different pools of nutrients in the soil. So this is the good stuff here in the middle, right? This is what plants are taking up, and how there are these different pools that feed into this pool of nutrients in the middle. We didn't talk too much about parent material today, but that is the material that soils are formed from. So rocks and minerals, as they break down, that's how we get soil. And this is a huge bank of nutrients. So, these are some examples of minerals down here: hornblende, potassium feldspar. And what a mineral is a repeating crystalline structure. of different elements. So you can write out a mineral in its chemical form, and then that's just repeated in this crystalline structure over and over again. So what you might notice for a mineral like hornblende, a lot of these elements that make up that mineral also show up on our fertility list. So as these minerals are broken down through weathering over hundreds of years, they're providing what we would call that innate fertility. So you can see that calcium, magnesium, iron, all that being kind of made available through physical and chemical weathering. The deal with parent material and weathering from rocks and minerals is it's a very slow process. So you can think of this as a huge pool of nutrients, but one that's just very slow. So as we harvest crops, we're taking nutrients out of the soil, and those are not going to be replaced quickly by parent material. You know, maybe over several generations, we might see some of that coming back. Organic matter is another source of nutrients. So if you think about things like manure or compost, there's carbon and nitrogen in there, but there's also sulfur, phosphorus, potassium. And this material we call the mineralizable pool. And that's because when these materials are in their free form, we call them mineral form. When they're in that manure or leaves or grass, we say they're in their organic form, and they're not immediately available for plant uptake. So they have to go through this mineralization process. And this is much quicker than parent material, but still probably on the order of a season or two. So if you make a big manure addition to your soil, you're going to see some nutrients that year, but you're going to see more the next year and the year after that. Okay, so the next pool to be aware of is what we would call the exchangeable nutrients, nutrients that are adsorbed to surfaces. And so this is an organomineral complex here. So that's our clay, primarily clay, and clay that might have some organic material attached to it. And that's going to account for the largest bulk of where nutrients can hang out if they're not in solution. And this is a really important component of fertility. So there's some nutrients that can be in solution, but there's other nutrients that are just going to hang out on these surfaces. And these surfaces tend to be negatively charged. So we're mostly going to be able to hold on to the positively charged ions here. This other pool here are soluble organic molecules, and they can account for quite a bit of surface area as well. So if there's a lot of organic material in the soil, and what happens with these organic molecules is all of the positive areas and what we say the water surrounding an organic molecule helps to create and stabilize these larger organic molecules by forcing the hydrophobic areas inside, and then they have these hydrophilic areas outside, and that provides lots of surface area for elements to attach to. So we call this the exchangeable nutrients. There's another word for that, which I would quiz you on if you could somebody could chime in. So the total number of nutrients, especially of positively charged nutrients that soil can hold. So again, positively charged ions we call cations. And so that total amount of positively charged ions that can be held by the soil minerals and the organic matter, we call that the cation exchange capacity. And so this is something that is highly influenced by those inherent soil properties. A clay soil is just going to have way more cation exchange capacity than a sandy soil is. If we add, so you've got a light colored sand and a dark colored sand. The dark colored sand is sand where we've added organic matter. We've built that soil. So you can really increase your cation exchange capacity, especially in a sandy soil, by adding organic matter. But those clay soils are still probably going to have more. An organic soil, that's like a peat bog. The definition of organic soil, I think, is it's at least 25% organic matter. So those are not soils that we see frequently. Okay, so I'm going to go into a little more detail real quick on that mineralizable pool, and look specifically at the nitrogen cycle. All right, so lots of bubbles and circles and arrows here, and I do apologize for that. But if we can follow along, so most of the nitrogen, well, so let's state that a different way. So here's the atmosphere. This is above ground. Most of the atmosphere is actually made of nitrogen. About 79% of the atmosphere is nitrogen, and it's in this form called dinitrogen, and it's not readily available. It's fairly inert. So we're breathing this material in, we're breathing it out. It's basically unchanged. But it's not biologically active. Some organisms can take advantage of that, and those are called nitrogen fixing bacteria. So through this mutualistic relationship with rhizobia in legumes, these organisms together are able to fix that nitrogen, bring it into the soil in a form that, or into their plant and microbial symbiosis in a plant that can be in a form that can be used by the plant. So they first are going to make ammonia, and then these different bacteria, nitrifying bacteria, can change that into nitrate. So earlier I alluded to nitrate being really common in the soil, and that's because as soon as there's ammonia around, as long as there's oxygen around, we're going to see this path happen from ammonia to nitrate. And then, so nitrate's great, plants love it, but one of the downsides of nitrate's negatively charged. There's not a lot of space in the soil to hold on to that negatively charged element, and so we can see some leaching from the nitrate. Okay, so we've got our organic matter kind of going into the system. So this was happening down in the roots. There's going to be some leakage of nutrients out of those roots, but most of that nitrogen that the legume is fixing, maybe a plant's just scavenging nitrogen from the soil, that's going to go up into the above ground biomass. So we're not really going to see most of that nitrogen until that plant goes into the soil, or until we got our little animal manures or compost being added into the soil. And so that's going into this box of sort of the soil organic matter. And it's not yet available to plants for uptake until the primary decomposers work on it. We mentioned that earlier, how we need those bacteria and fungi to work on that material. So they're going to eat the soil organic matter. We got our litter shredders hopefully involved in the situation, and they're going to build up their biomass. And then as these secondary and tertiary decomposers, things like the protozoa and the nematodes, they feed on those bacteria. They're going to release more available nitrogen, some of that ammonium, and then of course nitrate. And then finally, after all this happens, we get to these pools of nitrate, those available nutrients, and those can be taken up by the plant. So it's not an instantaneous process where we add organic matter and we get available nitrogen. We have to first go through that decomposition process. And so in order to help that along, we want to do things that help those organisms. Primarily feeding them the right thing is the best way. So we want to feed them a good balance of material that's got some nitrogen in it. That's why those, if we turn in, for example, a real woody cover crop late in the season, it's going to have too much carbon in it. And these organisms are going to actually take some of this available nitrogen just to get at that carbon. So it's important to feed a good balanced diet of more high nitrogen materials. All right, I'm going to move on into some key points to think about. So I hope you're writing down some questions. And you guys, I can't see the chat window, but we will hopefully have time to get to those. I've covered a lot here, and hopefully you can come back at me with some questions.
I will. I'll make sure
Okay.
at the end to ask any questions that have been put in the QA box or the chat. So go ahead and put them in as Doug presents. Thank you.
Yeah, this is hard without getting a little bit of feedback. Okay, so soil management, some key things that we should think about. So first of all, soil management should be a multi-year process that is constantly evaluated. You want to be able to understand the soil on a specific property so you can set realistic expectations. Again, that inherent versus dynamic. And then have specific goals in mind when considering different management strategies. And that gets back to that concept of a healthy soil. Like, what are the functions that we want that soil to do for us? So what are we trying to manage with soil? Again, I would have you think about this and maybe yell out some things that you would like to manage. And what are the tools that we have at our disposal? So we have the opportunity to add organic matter. We can add nutrients. We can irrigate soils, and we can till. So think about how all those different management practices might affect some of the soil properties we've talked about already. One key strategy for soil management is don't allow bare soil. There's a bunch of different widely agreed upon tactics for effective soil management, and this is one of the primary ones to think about and to implement. So bare soil contributes to soil erosion, and soil erosion is a major cause for nutrient loss and resulting environmental degradation. We've also seen examples of soil erosion causing dust storms and blackouts. This still happens. We know you think of this as the Dust Bowl of the 1930s. Well, still happens in the Columbia Basin of Washington. There are times when you can't really drive down the freeway because there's so much soil blowing around. And so just covering that soil will help prevent that. So ways to cover the soil are with cover crops, ground covers, and mulch. Mulches are the least effective soil cover, but are significantly better than bare soil. Soil covers protect the soil, but they also allow water to infiltrate at slower rates. And each one of these sort of has specific advantages and disadvantages. Cover crops are a key way to keep that soil covered. They protect the soil, they smother weeds, and they also take up excess nutrients. And legumes specifically add nitrogen to the soil. And in terms of organic agriculture, legume cover crops are actually a cheaper way to get that important nitrogen into the soil. So we talked about that nitrogen cycle. Legumes in organic ag, you're not allowed to purchase commercial fertilizers. So you have to find that nitrogen some way. And organic fertilizers, things like fish meals, bone meals, feather meals, those can cost $5 to $9 per pound of nitrogen, of available nitrogen, whereas legumes can get that same amount of nitrogen at $1 to $3 per pound. Now, a conventional fertilizer is going to be cheaper than that yet, but those prices do fluctuate with fossil fuel prices because that's how they are derived. So a few other things we're going to kind of dive into thinking about some of those organic materials that you might add to the soil or use for compost. The carbon to nitrogen ratio of those materials has probably the biggest effect on how they're going to behave in the soil. Things with a C to N ratio of 10 to 1 or less, we call those hot. 15 to 1 to 25 to 1 are cool. And then woody materials are over 30 to 1. So some examples of hot materials: fish and feather meals, poultry, fresh rabbit manure, seed meals. With these materials, it's easy to overapply them, lead to excess nutrient levels, potential to harm crop, degrade water quality. So some of these, like especially, a feather meal, you don't really think of this as an organic amendment that's going to improve my soil quality. You're thinking of that as a fertilizer, and how much of this do I need to apply to satisfy the needs of my plant, but not over apply. With these other materials that are in that 15 to 1 to 25 to 1, this could be more like compost, most manures, not chicken manure, but most other manures. So these are a little more slow release forms of nitrogen. They're going to provide nitrogen in subsequent years. And it's harder to kind of over apply them. You don't want to apply too much compost, but it's less likely to lead to nutrient leaching. And then woody materials are things like straw, sawdust, paper waste, horse bedding, leaves. As I alluded to a little bit, if you apply something like that woody cover crop or straw, it can lead to what we call nitrogen immobilization. And that's where in the nitrogen cycle, we've got a pool of available nitrogen. Those microbes are going to suck up whatever nitrogen they can find in order to decompose these woody materials. And they're immobilizing nitrogen. They're putting it basically from that mineral form back into an organic form, at which point it's no longer available. So this is just an overview: reduce tillage, improve crop rotations, cover crops, organic matter. I'm going to move on. Soil testing. Okay, why do we sample soil? You're all thinking, I hope you're thinking, why do we sample soil? Well, it's hard to look at soil and know what's in it. That's one of the main reasons. The most robust testing we have is on the soil fertility front. And so, it's difficult to look at your soil and know what's the phosphorus level, what's the potassium level. We need to get a soil test in order to evaluate that. And then in terms of making that soil testing, there's different approaches. This would be what we call a systematic test. So you could sample from many different points. This looks very expensive. Random sampling. And then what I like to advocate would be what we call a stratified random sample, or you could also call this a management zone approach. And so here you think about your field. So again, the soil is heterogeneous. And then you might have, so it would be good to put, take some soil from here, some soil from there, and then you can start to manage that soil fertility based on what you're finding in your soil test rather than taking one soil sample for the whole area. This shows a little bit different way to think about that. So you've got some crop here and some other crop here. They're in different parts of the landscape. You would not want to sample this area, combine it with this area, and send that off to the soil test lab. So sample this area separately, and then get the results from that. This highlights that concept of inherent soil properties and setting your expectations. Soil quality, some parameter here, maybe that's organic matter. So soil A has got a much higher organic matter just inherently. And your goal for soil A may be to, just maintain that organic matter. With soil B, your goal may be to raise that organic matter. So you want to sample, one soil test is just a snapshot in time. So we want to sample multiple times, and you can see how whatever parameter it is we're trying to follow is changing through time. Okay, so when we send that soil off to the lab, what we're doing is they're going to use a chemical extractant. You don't really have to know too much about that, but just understand that what they're trying to emulate is that available pool of nutrients. We're not concerned when we send a soil sample off to the lab about what's in the rocks and minerals, that parent material. That's not going to ever become available to us. And we're also not necessarily at this point concerned too much, or at least most fertility labs are not. They're giving us some information about mineralizable organic matter, what's in the organic matter. We're getting better at that, but for the most part, we're really just focused on that, what's available. And these are some different soil test reports, just to kind of give you an idea of what they look like. We often see some bars, and I'm going to talk about what this means here in a second. Okay, so what do those bars mean? That, there is this bar graph here. Low, see if you can see this: very low, low, medium, optimum, very high, right? So that's what we're seeing oftentimes from the soil test. We've got the raw number here, what was in the soil, and then this is our interpretation. And so somebody's saying this one is optimum, calcium's optimum, but phosphorus is low. So what low means is that if you were to apply that nutrient, you're quite likely to increase crop yield. Medium, maybe you will, maybe you won't if you apply more of that nutrient. And if you have a high soil test value for something, there's no or very little chance that applying more of that nutrient is going to increase crop yield. So high does not mean that you've got a toxic amount of something. It just means you're all good. There's plenty of that nutrient there. You don't need to go out and apply more of it. So these are some of those extractants that I mentioned. Again, you don't really have to know them. One of the key things about the extractants, you may have heard this adage of, sort of pick a soil test lab and stick with that. This is one reason, because different soil test labs do use different extractants. So you can't compare the results from phosphorus is a big one, where you can't compare the results of a Bray phosphorus to a Malick or an Olson. And so that's one plug for using kind of a local soil lab, because they'll know how to interpret that extraction. And then what the extractants are doing is trying to figure out these pools here, right? So not only what's in the solution, but those extractants are trying to knock off the nutrients from the surfaces, and then telling us what's likely to be available from both in the solution and from the surfaces. I'm just going to run through these because I think you can get this from other sources, or soil labs will typically interpret this for us. These are what they're, well, a low value of potassium often will come with this is how many pounds per acre you should apply to meet that need. Okay, pH, we talked about that a bit. And an important concept for pH is the buffer pH. So a question I get a lot is, can I just use a soil test kit that you could buy somewhere? And in general, those are not as good. And pH is a really easy thing to test with just pH paper. But one of the problems is it doesn't tell us how to resolve a pH problem. So in my area of the world here, we have a lot of problem with acidity, soil acidity. And so a lot of times we'll get the pH test, and then we also get what's called the buffer pH. And the buffer pH is going to be another number that tells us how hard is it going to be to change the pH. So this soil here has a high reserve acidity. This soil has a low reserve acidity. And so they both would have the same pH. So the hydrogen ions here in solution are the same. So these soils would both have the same pH reading. But when they do the buffer test, what they do is they neutralize the pH, they neutralize the hydrogen ions that are in solution, and then this soil has more hydrogen that's going to come off solution or come off the surfaces, and we haven't changed the pH much. Whereas this soil, much less lime requirement in order to change the pH. So those words, buffer pH, lime requirement, we're talking about the same thing essentially in those cases, and that's a very important part of testing for soil pH. And then this is my last slide, and we talked about cation exchange capacity already. You can change cation exchange capacity. This will come on a soil test as well. And you can change this through additions of organic matter, but it's not easy. Again, this is highly related to inherent soil properties like soil texture. And I will stop there. I wonder if I can pull up
Well, thank you for that presentation. We have a lot of questions that came in, Doug, and I'll go ahead and read the questions.
I can see the window too now.
Okay, so I'll start with the ones that are in the chat because you're probably seeing the one in the Q&A. And so in the chat, Travis asks, I have a general question. How healthy productive is native land before adding anything to it? My land is typical high desert, sagebrush, and other similar native grass. There's a lot of organic material decomposing on the top and not too much sand and rocks. Thank you for your thoughts and time.
Yeah, that's a great question. I think that, again, so think about the things that go into productivity, fertility and soil tilth in that little hierarchy that we created. That tilth and fertility were kind of at the bottom. And then there's a bunch of other things that can affect productivity, climate, light. So your soil, this is why the Columbia Basin of Washington is so productive. Basically, that's a desert, but it's very hot. There's lots of light, and we were able to add water, and we add a lot of nutrients to make things grow there. So, the sandy sort of desert there, I've done quite a bit of work there and textured those soils out. And I mean, it is like beach sand in some places. It's, it's heterogeneous around the basin, but um, that beach sand has very low organic matter, very low nutrient holding capacity. But one can come in with the right resources and farm that and turn that into a very productive resource by adding water, by adding nutrients. And you can do that all carefully, right? You don't have to over fertilize it. You can fertilize it carefully. You can do things to add organic matter, growing cover crops on there. But water, water is going to be kind of that key element that's going to distinguish that native, dry, arid environment to something that's more productive.
Thanks, Doug. What's an ideal percentage of organic matter in the soil?
I don't think there is one. I would just say that you can have too much organic matter. And what starts to happen when you have too much organic matter is you can get kind of waterlogged soil. So the organic matter is so good at holding water, that you start to prevent oxygen from being able to get in there. There are some pests that really like high organic matter, like symphylans. But I know farmers that have 20% organic matter. They love their soil. They keep adding it. So I don't think that there is a magic number there. And then I'm also interested in, and have gotten more interested lately in anthropogenic soils. So we have that in the soil forming factors, but human made soils is kind of a new area and a new way to think of things. And I built a rooftop garden last summer, and I did a lot of research trying to find what kind of material to put in there, and it is very high in organic matter. I guarantee you. And I put some in a container and grew some tomatoes in there, and they grew great. So there's actually a new word in this whole anthropogenic soils thing called organoponics, and that's essentially growing in compost. So I think that there's no perfect number. Whatever your soil is, whether you've got really sandy soil or a really clay soil or a really organic soil, it's going to affect how you manage the soil. So a sandy soil, you need to water it a little more frequently, maybe less each time. Otherwise, you're going to leach things out. Clay soils, you can water less infrequently, and so they all kind of have their trade-offs.
Thank you. We have another question, and Victoria says that she has a backyard garden and her soil is desert concrete. She says she's added mulch to the top to try to improve the soil. What else can she do to improve its tilth?
Yeah, that's a great question. This is one of the conundrums with tillage. So you could, incorporate organic matter into that soil, and you would probably see a pretty big increase in productivity. Um, can you get all that material, that organic matter, into the soil, without incorporating it? You'd have to get plants established, lots of cover cropping, probably trying to use cover crops that were going to break up the soil. So it's just a much faster way to kind of make to incorporate organic matter, even if it's just in the top couple of inches. That'll have a huge effect. Most of the action for roots is happening in that top 4 to 6 inches. So you don't need to improve your soil very deeply. If you have a hard pan that's preventing, for example, water from infiltrating, that can be an example where you need to do something a little bit deeper. But if your soil's well drained, just starting out with improving that top 4 to 6 inches, and then with an addition of a couple inches of organic matter in the form of compost or manure, and then over time using cover crops, things like that are going to just continue to maybe improve soil a little bit lower down and maintain that health in the top couple inches.
Doug, following up on that explanation, we have a couple questions about the availability of nitrogen. And so one question is about mulch, how to mulch in a way that will control weeds but not essentially bind that nitrogen. And then the other question is, when using legumes to fix nitrogen from the air, does that nitrogen stay with the plant? So for instance, if you pull out the plant at the end of the season, are you taking the nitrogen it fixed with it?
Yeah, that's a great question. Yes, you can't sort of have your cake and eat it too. So um, with cover crops, we call cover crops. I used to call them a gift to the soil, but there was a great, I think, New York Times Magazine article on cover crops a couple of years ago, and the author called them a facial for the soil. So, but it's that concept that you're, with a legume cover crop, you're really growing that crop for to improve the soil for another crop. So you need to turn that, and the best time to turn in that cover crop is right at flowering, and that's when you're going to have kind of the height of nitrogen in the above ground and in the roots, and you turn that in, and then that nitrogen is going to be available to the soil. So if you wait, say you've got like a pea, because you can use peas as a cover crop, and then you wait for those peas to make new peas, and you want to harvest those pea pods. What Nitrogen is highly mobile inside of plants, and plants are going to take that nutrient, and they're trying to consolidate it for the next generation of the plant. So they take as much of that nitrogen as they can and put it into the seed. That's why seed meals make good fertilizers, and that's why, on a low meat or vegetarian diet, you really got to look for those legumes to get that protein, because that's essentially in the body nitrogen. That's where we find a lot of protein is high in nitrogen. So nitrogen is high in protein, whatever. So anyways, that's where the nitrogen is going, into those beans, into the seeds. And so you can't harvest the seeds, and then you're taking, a good 75% or something of the nitrogen away from the soil if you do that. Some crops, broccoli is one that, broccoli just loves nitrogen, brassicas, and then you harvest that little part of the flower, but there's still a lot of, bodacious leaves and things left. So you're going to get more of a nitrogen bump from like that broccoli residue than you would from wheat, obviously, for example. So there's an amount of nitrogen left in the residue. But if you're taking and harvesting something, you are taking a good amount of it away. And then the other question was around mulching. And so, yeah, mulches, if you are mulching with some high carbon material, don't incorporate it into the soil. If you just leave it on the top of the soil, it's not really in any great amount going to do any kind of immobilization. And also, size is really important. So if you're mulching with straw, those are relatively large pieces that aren't easily colonized by microorganisms. I mean, the organisms can basically just colonize the outer surface. Now, if you took sawdust or something and put that on your soil, lots of surface area, a lot more potential for problems there. But still, if it stays on top of the soil, it's not going to have that same immobilization effect. And then I saw there was a question about, is immobilization permanent? And the answer is no. I mean, it depends on how intense the imbalance is. If you just, so some composts can be in that 25-1. It's actually very common for like a commercial compost to be the 25-1 C to N, and that's right on the border of where we would see immobilization or not. And so you can apply compost thinking you're doing something really great and actually see a short-term immobilization, 3 to 4 weeks even, and then that will kind of go away. So it really depends on how extreme, the imbalance is.
Great. I think we'll take one more question. And there is a question about looking at soil and earthworms. And where can we get, besides earthworms, um, sorry, I'm going to repeat this. Where can we get, besides earthworms, or how can we attract soil biological engineers? So essentially, how can you attract those organisms that are going to be breaking down the plant material and then making available the nutrients to the plant?
Well, yeah, so earthworms are in a category we call ecosystem engineers. And then the shredders and the litter dwellers, Those are like the Columbella, um, millipedes, things like that. Um, earthworms, I guess you could move them from, I think that it'd be likely. I don't know. I've never looked into inoculating soil with earthworms. I know you can do that. You can buy them. You want to be somewhat careful about that. Um, but I know that's possible. Or you can move, maybe moving some good soil to some other soil. You're probably going to get some cocoons in there. But they are, if you already have some earthworms in your soil, just reducing tillage will certainly increase their numbers, and we've seen that again and again in our research. So, and then the timing of tillage is really important. So, in our environment, when it's really wet in the spring, the earthworms are up high in the soil. And so that spring tillage, when it's really wet, has the greatest effect on earthworm populations as opposed to tilling in the fall when it's drier and the earthworms are much deeper. We've seen, surprisingly, that fall tillage did not affect earthworm populations. And that was a surprise to me. And those microarthropods, yeah, their numbers. So the other thing about soil is it is resilient. So we can see with the microarthropods, when we till soil, their numbers just drop very much compared to some nearby place where you didn't till the soil. But after 8 months, they're back up to where they were before. So that's, if you go into like a pasture or something. So that's a testament to the resilience of the soil and the soil biology specifically. So they will come back if you've tilled them. So I think if you look at it over a long term, trying to reduce disturbance, both the intensity of disturbance and the frequency of disturbance over the long term, is a beneficial approach.
Thank you, Doug. Thanks for answering all those questions. I did put some resources related to soil testing and management of soil in organic systems into the chat. We'll make sure that those are also linked where you'll find this recording. So we would really appreciate your taking our post-webinar evaluation, completing that. A link is automatically going to launch for you when you close out of this webinar. You'll also receive that tomorrow, and we're going to provide that feedback to Doug. And we also use that to identify what our topics are for our webinar series. So this entire webinar series that we're having this year is based on past evaluations and priorities that people identified for what they would like to learn more about. We also, on our Cultivating Success program, have our recorded webinars, which include a couple that specifically address cover crops. So those might be of interest to you. Our upcoming webinars this month with our theme of digging into soils and compost are looking at composting for small livestock producers. So this is a great addition to the framework and the information that you provided, Doug. Then we'll also be talking about biochar, its properties, and the potential as an agricultural amendment. And then closing out the month with vermicomposting, talking about vegetable kitchen scraps to usable compost. I also wanted to say that as we move into March, we're going to be looking at pest management and insects. And Diane Green, who is a farmer in North Idaho, she actually did a trial on her farm looking at no-till, and she created the perfect habitat for wireworms and is now engaged in a research project about wireworms. So if you're interested in kind of thinking about no-till and some of the potential benefits and challenges of that, I encourage you to register for that webinar. She's working with several soil scientists and plant pathologists at University of Idaho in that research that she's doing on her farm. Doug, thank you so much for joining us today. This was a great webinar, and this will be recorded. We appreciate your time and look forward to having you on again in the future.
Thank you. And yes, I would appreciate very much to hear the results of evaluation. So please take the time to do that.
We definitely will get that out to everyone and back to you. So thank you, everyone, and have a great day.